110.
אבל זה לפחות על דעתנו? כלומר, מישהו היה
אז אנחנו מנסים למנוע את זה, כי אנחנו רוצים לעשות שם את סמינר יורם.
אבל לא יחליפו לנו פתאום את אני יודע, את הלוחות בלוחות לבנים או את הכיסאות בכיסאות זכוכית, כאילו לא יהיה איזה משהו...
אני מניחה שיעל מודעת לזה.
זהו, אני מקווה.
צריך עוד משהו פה?
לא, אני אצליח למצוא מי ידבר.
אוקיי. אז אני רגע הולכת לשם לארגן את ה...
כן, נראה לי שלא צריך מפה, נכון? זה נראה סביר. את זוכרת אם זה רק על שם פול ארדש או גם על אנה? ההרצאות הן על שם פול ואנה ארדש או על שם מי? זה על שם פול או שם מי? יש את ההורים שלו? הייתה איזה תרומה פעם? את לא יודעת מה... אין לך מושג.
אני יודעת שזה על שמו.
על שמו, על שם פול ארדש על שמו.
Just like, you want coffee or tea or something?
I'm good.
You're good?
one important thing, this there 23.9 is the temperature. It's not the time.
Okay, the second one is...
Often people look at that and say, oh, I have 23 more minutes or 2 minutes, so this is just temperature. Nobody knows why we have it.
Maybe, I don't know, it might be better if you wear a microphone.
Sure.
Okay, shall we start? Not according to the universal clause. Yes. Okay, thank you very much for coming. Today we'll be starting the first lecture of the Paul Erdős lecture series, which we are holding since 1998, 3 years after the passing of Paul Erdős. You probably know Erdős and his achievements, and this has been a joint lecture series together with computer science concerned with discrete mathematics and the theory of computer science. We've had the pleasure of having many distinguished speakers, and let me ask Noam Lifshitz to introduce today's speaker. So please, Noam.
So it's an honor to invite Mehtaab to give these 3 talks. He has so many contributions to extremal combinatorics and additive combinatorics, number theory, random matrix theory, and probably other fields that I'm not aware of. And it was really, I'm really happy to have him here in this time of war that he agreed to come. And and it was important for Hillel to say that Szemerédi's theorem was mentioned first 50 years ago in this colloquium. Okay, so you have a microphone. Okay.
Okay. Hopefully people can hear me. Okay. Yeah. Great. Yes, it's a great honor to be here, and today I'll be discussing improved bounds for Szemerédi's theorem. And everything I'm discussing today is joint work with James Lang, who's at UCLA, and Ashwin Shah. So, okay, let's sort of set up what we're discussing. So the main object of the talk will be the size of the largest set, avoiding k-term arithmetic progressions. So let Rk of n denote the size of the largest subset S, which is contained in bracket n. By this I just mean the first n positive integers with no k-term AP. So AP is just short for arithmetic progression, and just to be completely clear, a k-term arithmetic progression is x plus y, x plus k minus 1 times y. And in order for this to be non-trivial, you need y to not be equal to 0. So the first people to ask about sort of trying to understand the behavior of Rk of n were Erdős and theorem. They asked in 36. Essentially, they asked, is Rk of n, is this little o of n? So throughout the talk, one should think of k as fixed and n tending to infinity. So you should always think of k as an absolute constant. So the first progress on this conjecture was a theorem due to Ra in 53, where the case k equals 2 is trivial. So the first non-trivial case is k equals 3, and Roth gave an upper bound. He proved that Rk of n is at most discrete math, so I'll use the symbol. So this means I'm just hiding an absolute constant. It's n divided by log n. So not only is it little o n, but he gave some quantitative rate. I think a further roughly 20 years later, Szemerédi resolved the conjecture of Erdős and theorem. So in 69, he did the case k equals 4, and in 75, he did the general case, and he proved that Rk of n is little o of n. And in particular, that's why this is called Szemerédi's theorem. There have been many subsequent proofs, so there was particularly influential proofs, especially given the topic of the lecture by Furstenberg in 77, where he gave an alternate proof of this. But both the proofs of Szemerédi and Furstenberg really don't give good rates. I mean, so Furstenberg's proof uses ergodic theories, doesn't give any rate, and Szemerédi's proof, if unwound, gives atrocious rate. So you're not saving very much over the trivial bound event. You're saving some growing function, but it doesn't grow very fast. And it's sort of interesting to understand how fast that grows. So, so in the case of R3n, so sort of the first time we knew this was little n, we already had a quantitative bound. But it's sort of interesting to understand what is the quantitative rate here. So the question of bounds for R3 of n was attacked by many authors. So Roth's result was first improved by Szemerédi, then Heath-Brown, then Szemerédi, then Bourgain twice, then Sanders twice, then Bloom, then Schoen, then Bloom-Sisask. But I mean, okay, maybe most spectacularly and quite recently was this beautiful work of Kelly and Mehtaab, which said you can save a quasi-polynomial amount over the trivial bound. So R3 of n is at most n times e to the minus log n to some power. I think they get the power of 12, but okay, just they save some power. And this is 23. Yeah, this is 23 plus. And I mean, this is particularly impressive given that we know a lower bound, which is much older, a lower bound of Barron from 46 gives that R3 of n is bigger than n times e to the minus some constant times root log n. So up to knowing exactly what this power of log n is in the exponent, we understand the case of k equals 3. However, so for k greater than or equal 4, so much less is understood. So for a long time, there was sort of no, really effective version of sort of saving some effective bound over the trivial bound of n. So it was a major accomplishment of Gowers. First in 98, we needed the case k equals 4, and then in 01, we needed the general case where you prove that Rk of n is at most, so there's no hiding constants, n times log n to the minus 2 to the minus 2 k plus 9. So he gives an explicit value, and so yeah, so this is what he proved. But okay, so this is roughly the shape of what?
Can you provide this minus 2 to the minus 2?
To the k plus 9. It's just some constant. This is unimportant. Yeah. It's just some constant depending on k. But he writes down they're like this is an inequality for all numbers n. So it feels if you work so hard to not lose any constant factors, then it's important to write it down. So this was sort of the state of the art for general k, except for one exception. It was work of Green and Tao. I'll quote their last bound, which was in 17, where they sort of showed that R4 of n is at most n times log n to some minus c, so for some constant c between 0 and 1. So maybe the main result of the talk is sort of improving Gowers' bound for general k. So what we show is that there exists ck greater in 0, 1 such that Rk of n is at most n times e to the minus log n to some power ck. So so this is less, so So you're saving less than any power of a logarithm, but you're saving more than any power of a double logarithm. So it improves on Gowers' bound, but say it doesn't improve the work of Green and tau. So the rest of the talk will sort of just be a discussion of, this is a rather, this takes almost 200 pages to prove, so we're not going to really, I want to discuss sort of the strategy behind how one starts to think about this problem. Sort of, the real goal is to explain the strategy to KAPs via Gowers norms and then sort of maybe, I think the thing that's most surprising to me about this whole line of work is that this is, as stated, it seems like a purely combinatorial problem, but somehow we now understand that there's some algebraic structure behind the problem. So in particular,
Sorry, can you take a second? Is there anything interesting in terms of lower bounds for
so the lower bound is, so a lower bound for R3 of n is still a lower bound for Rk of n, but it's slightly better. So I think the lower bound known is something like, it's some power that, so you can take so you can always take square root log n, but you can take some better power, right? I think it's this, but don't quote me on it. Yeah. So where,
it's essentially Baron.
yeah, you can do better than Baron using the fact that you're avoiding KPs, and I think most people would. I certainly am happy to conjecture that this is much closer to the truth. Yeah, this is a consequence of our bounds, and not. I don't think this is somehow a natural. There's a reason why this bound is somewhat natural given the proof techniques, but I don't think it has anything to do with the truth. I think it's a limitation of the proof. Yeah, okay. And sort of, okay, so my goal is really to maybe get some vaguely precise statement of what this algebraic structure is, and sort of maybe discuss that. Okay. So probably not everybody is familiar with the Gowers norm. So okay, another convention that throughout this talk, I've set everything up to be in terms of the first n positive integers. For various technical things, it's more convenient often to work in the cyclic group Z mod NZ. One should think of these two settings as completely equivalent. They're almost completely equivalent. So first, let me define the Gowers norm. So let's consider a function f from Z mod NZ to C, which is sort of one-bounded, and let n be prime. This is so I just don't write false statements. Okay. So it's important to define what's called the multiplicative derivative of f. So the multiplicative derivative of h at x is just f of x times f of x plus h bar. This is the complex conjugate. So the Gowers norm is some average of this form. So the Gowers UK norm to the power 2k is the average over x, h1 through hk, delta h1, delta hk, f of x. Okay. It shouldn't be this is the Gowers UK norm. It shouldn't be obvious that this is positive or that's a norm, but these things can be proven. This compact formulation is a little bit difficult to parse, so maybe it's useful to write out the case of the U2 norm, which is the simplest norm here. So it's the expectation over x, h1, h2 of f of x plus h1, f of x plus h2, f of x plus h1 plus h2. So sort of you're taking your function f and you're averaging it over these parallelepipeds. So like x plus h1, x plus h2, x plus h1 plus h2. Okay. So this is, I mean, as currently stated, is just some definition. So as stated, I mean, it's not clear why this has anything to do with the problem, but the starting point here comes from a lemma of Gowers. So let fi be functions from z mod nz to c, and delta be in 0, 1. So if we're going to study k-term arithmetic progressions, it seems natural to try to understand what happens when, say, the average f1x, f2x plus d, f3 x plus 2d. So I'm sort of taking some weighted count of 3-term arithmetic progressions, and I'm supposing that this average is large. Then what I'm going to be able to say is that f3 has a large Gowers U2 norm. So then f3 U2 is bigger than delta. Okay. And once you state this lemma correctly, it's sort of the short chain of Cauchy-Schwarz. So I'll show this once, but it's several applications of Cauchy-Schwarz inequality. So first, by applying triangle. Oh, sorry. These fi are one-bounded. Okay. So let's just go through this once. After this, I will not bore you with Cauchy-Schwarz. So if you apply the triangle inequality, we get that delta is less than this average.
So again, you have function f1, f2, and f3.
Yeah.
This inequality, and the conclusion is about f3.
Yeah. So I can make it about any of these. I'm going to prove it to you for f3. I mean, they're sort of symmetric, basically. So in particular, I'm taking completely arbitrary functions, and a priori I don't know anything, and I'm saying I have some structure on it. This is somehow like, yeah.
But the condition resemble arithmetic progression.
No, I mean, it's exactly weighted arithmetic progressions. It's not, yeah. Okay, so you do Cauchy-Schwarz once. So this average becomes expectation of d1, d2, f of x plus d1, f2 of x plus d2, bar f2 of x plus 2d1, f2 of, or f3 of x plus d2 bar. So I've applied Cauchy-Schwarz and then expanded out. If you do a change of variable, this becomes the expectation over x, d, and h of del h1 of f2 of x, del 2h of f3 x plus d. So this is some change of variable that I'll have you believe me, but okay, it sort of this kind of like squaring operation sort of starts to give you things that look like that multiplicative derivative. And if you do Cauchy-Schwarz one more time, which I'm going to omit, you get that this is bounded by the U2 norm. So I didn't really show the calculation, but okay, it's 2 applications of Cauchy-Schwarz, and you prove this fact. Okay.
May I ask, I lost to somebody, what is that? Given f, what is f1 and 2 f?
So okay.
Oh, it's 3 functions.
Yeah. So I just wrote fi. Sorry. Yeah. So just let 3 functions be such that one bounded. Okay. Okay. So far, this doesn't seem particularly useful. I've just sort of converted one condition into some other condition. So I've converted that my 3-term arithmetic progression count is sort of off from what I expect, and I've said my function has large Gowers norm. It's not clear why this should be useful, but it turns out it is. So, okay, maybe to demonstrate why this is useful, let's sort of give a proof of Roth's theorem. Proof here should be interpreted liberally. So, just for our setup, suppose we have a set A in Z mod NZ, and the size of A is alpha times n. And we're assuming that A has no k-term arithmetic progressions. So, or has no 3-term arithmetic progressions. So because it has no 3-term arithmetic progressions, we essentially have that the average of the indicator of A at x, the indicator of A at x plus y, is the indicator, or x plus d, indicator of A at x plus 2d, that this is essentially equal to 0. I'm slightly lying. You have some contribution from d equals 0, but OK, you can pretend it's essentially 0. So we don't want to directly apply the proposition. There's a trick. What you do is that instead of looking at the indicator function of A, you look at what's called the balanced indicator function. So you take indicator A of x, indicator A of x plus d, the indicator A of x plus 2d minus alpha. So if you work this out, so I'm just subtracting off the mean. And when you subtract off this mean, it turns out the contribution from this alpha times these two terms, this factor, so it's alpha cubed. So this average is roughly equal to alpha cubed. And if you're careful about it, because I put a slight lie here, okay, it's bigger than alpha over 2, alpha cubed over 2. Okay, so now we're in position to apply the lemma. And so the lemma gives that the U2 norm of the indicator function of A minus alpha, the U2 norm, this is bigger than alpha cubed over 2. Okay, so we have this norm is large, but a priori, it's not so clear that this is so useful. So why is this useful? This is useful because of the following magic formula. So for any function f, the U2 norm to the 4th power, it's the same as the L4 norm of the Fourier transform. So because the Fourier transform isn't going to show up for the rest of the talk, this is just a formula, and you can verify it using orthogonality of characters. And okay, by using Parseval, this is at most the L2 norm of f times the max over psi of f hat of psi squared. So you can combine this, and you know since this function is bounded by 1, you can derive that the indicator function of A minus alpha, the maximum Fourier coefficient of this, this is bigger than some power of alpha. I think if you work it out, like alpha cubed. Okay, so let's write out what this means. This means that if you take the maximum over psi, the expectation of the indicator of A minus alpha at x times e to the 2 pi I psi dot x over n, that this is bigger than alpha to the 1. So we've turned this condition of having large U2 norm into correlating with some sort of very nice function. So in this case, a Fourier character. And given this, you can do what's called the density increment strategy. So A has increased density along a long arithmetic progression. And okay, so once you know that you have increased density along the long arithmetic progression, you restrict your set A to that arithmetic progression, and then you keep running the strategy. Eventually, the set can't have density bigger than 1, and you use that to drive a contradiction and to prove Roth's theorem. So I don't want to go through the end, just to say that the key point here is that we've converted this U2 norm being large into the fact that your function correlates with something very nice structured, in this case a Fourier character.
So this character tells you which arithmetic progression to do.
Yeah, you use the character to figure out which arithmetic progression to look at. Exactly. So, okay. So, I mean, this whole subject, the subject of Gowers norms also goes under this term. So, it goes under this term higher order Fourier analysis. And I think my interpretation of what this term means is that sort of how do you replace star? So in particular for the U3 and higher norms, Fourier analysis is insufficient. So really what our goal is that if we know that the U2 norm or the U3 or U4 or U5 norm is large, we want to say something meaningful about the function given that hypothesis. We want to say something useful. In this case, we said if the U2 norm was large, we correlated with a character. We want to find a replacement for that. And
So just to make, if you look at this quantitatively, this gives you what theorem with which bound?
this gives you the log bound.
The log.
It's log, maybe log to some power, but in some sense this is equivalent, almost equivalent to Roth's original proof. But I phrased it in a way so that these, the analog of this proposition sort of translates almost identically. So if you, instead of having 3-term progressions, have weighted 4-term progressions, then you get the U3 norm. If you have 5-term progressions, you get the U4 norm, and so on. So that lemma stays the same. The Cauchy-Schwarz works much the same way. But sort of how you understand when this norm is large changes. And that's the battle. So, So the real work in Gowers' papers is to sort of say something useful under these conditions. So what he says is sort of, if the UK norm of f is bigger than delta, then f has increased density along has increased density along a long arithmetic progression. And long here means just some power of n. So n to some power ck. And sort of given this, you can sort of run the density increment strategy and give a bound for Szemerédi's theorem. So this is sort of, this is one conclusion you can derive, but it's not an if and only if. So the reverse direction is not true. So in particular, what you can have is that you can have increased density along some long arithmetic progression like this, but you will not have increased Gowers norm. And sort of,
So can you hint how this leads to this tower dependency between Gowers?
So the tower is just like of the power of log, so you shouldn't worry about that tower. Just think of that as some constant ck. That's. The fact that you get log is from the fact that you're passing from n to the ck. That gives you the log type balance. In particular, this arithmetic progression is like length n to the 1/2, and it's almost exactly the same. So maybe the next task here is so let us try and formulate the reverse direction. Okay. So let's first just do the U2 case. So let's try to understand when the U2 norm is equal to 1. And sort of if it's equal to 1 and it's a one-bounded function, then you can write f of x as e to the 2 pi I over n times g of x for some function g, which takes values in the reals. And it's also convenient here, so we had multiplicative derivatives. It's useful to have additive derivatives. So the additive derivative of g of x is just g of x minus g of x plus h. And the reason this is a useful definition is del h of f is e to the 2 pi I over n del h of g. So exponentiation sort of changes the multiplicative derivative into an additive derivative. Okay, so let's write out what this condition means. So if you write out this condition in terms of g, this implies that del h1, del h2 of g of x is equal to 0 mod 1 for all x h1, h2. And okay, so this is saying that if I take my second finite difference of my function, it's always equal to 0. And it turns out to be pretty easy to classify such functions. So all functions of this form are like, they're linear functions, ax plus b mod 1. And okay, if you take e to this thing, this is exactly what a linear character is. So this is one way of sort of guessing that the inverse theorem for the U2 case is sort of correlation with some kind of additive character. So you can try doing the same thing for the U3 norm. So you can sort of look at when the U3 norm is 1. And if you do this, the condition, instead of becoming del h1, del h2, it's del h1, del h2, del h3 of g of x is congruent to 0 mod 1. So I'm taking the third partial derivative of g, and it's always equal to 0. It turns out, so okay, in this case, it's a linear function. So it turns out the natural thing is true. So g here always has to be ax squared plus bx plus c 1, 1. So, okay, in the U2 case, we knew, what did we actually prove? What we proved is that if the U2 norm is bigger than delta, then you correlate with something which has U2 norm 1. So the natural guess would then be that if your U3 norm is bigger than delta, then you actually correlate with a function, which is the exponential of a quadratic. The reason this, the reason this subject sort of is interesting is this, so this naive guess is false. So first I'll give a more down-to-earth description of why this is false, and then give the way one should actually think about this. So let's sort of consider the case where the U3 norm, say, is 1 over 100. But we still have that f is e to the 2 pi I times g. In this case, we no longer lead that this identity that the third partial derivative of g is equal to 0 holds all the time. So it's sort of sufficient if del h1, del h2, del h3 of g is roughly equal to 0 mod 1, 1% of the time. And the point is there are actually very different functions g which satisfy this. So the crucial example in the subject is the following. You take root 2 times x and root the floor, so this is the floor part of root 3 times x, and you take this mod 1. And the floor function, it's not additive. So it's not true that root 3 of x times floor of root 3 of x plus h equals root 3 of x plus root 3 of h. But this holds half the time. And so because this holds half the time, this third partial derivative, this kind of acts like a quadratic then, and then it vanishes 1% of the time. And this function, e to this function, is genuinely different than any quadratic. It will not correlate with any quadratic. So this is a genuinely different example, and okay, the theory sort of has to account for this. So it's in particular, it's not a completely arbitrary function. As Gil suggested, we will now give this the name bracket quadratics. And okay, for the rest of the talk, I will use this notation of bracket polynomials. So when I take e to some expression like this, I'll call it a bracket quadratic, and if it's degree 3 in the obvious sense, I'll call it a bracket cubic, and so on. But this is, it turns out this is not the right way to think about these objects, even though this is how we'll discuss them. So really, so the correct way to think about these objects comes from ergodic theory. So there's a long list of names here. So the first people to realize this were Furstenberg and Weiss in some closely related contexts. There's also work of Constantine. Ziegler, Bertelsen, Hosekra. So there are sort of multiple names. I'm not going to precisely state any theorems proved in the ergodic literature because the statements look different. But I think it's fair to say the ideas are very heavily inspired by what occurs there. Okay, I leave myself enough room. So the right way to think about these is as examples coming from sort of nilpotent Lie groups. So the simplest case is the what's called the two-step Heisenberg group. So this is a group G of upper triangular, 3x3 upper triangular matrices with ones on the diagonal. You have a discrete group inside of it, which is when these three entries are all Z. And okay, so this is what's called a three-step nilpotent group. So if you take the commutator of G, you get the following abelian subgroup. And if you take one further commutator, it vanishes. So you just get the identity. So it's a two-step group. So we're going to look at an element 1, 1, 1, and we're going to give it elements A, B, C to its entries. And I'm going to define a function on the group F, which is just this is e to the 2 pi I. So you have minus A floor B plus C. So at present, this is just some function on the group that I've defined. But it turns out to be invariant. So what you can observe is that if you take f of g times gamma, this equals f of g for all gamma inside the discrete group. So in particular, if you sort of right multiply by this element, it sort of the values stay the same. So you can sort of think of this. So it's perfectly valid to think of f as a function of the quotient g mod gamma to c. And it turns out the sort of right thing to look at is to, instead of just looking at a single element, to sort of look at polynomials of the element. So you look at f of g to the n, so I'm raising g to the power n, and okay, if you look at this, this turns out to be e to the minus a n for bn plus some garbage, cn, ab, and choose 2. And okay, that looks exactly like the bracket quadratic over there. So this kind of algebraic construction gives these bracket quadratics. And in general, the right objects to look at are functions sort of on, like you take a nilpotent Lie group, you quotient by a discrete co-compact subgroup, and then you look at functions. You sort of look at, you evaluate polynomial maps against that function. This, however, takes quite a bit more machinery to set up properly. So for the rest of the talk, I will just use the language of bracket quadratics. Even though, I mean, this is sort of the right way to think about these objects. So the main theorem in this subject, okay, I'm going to put stars because the statement is very imprecise. This work of Green, Howe, and Ziegler. They did the U4 case in 2011 and the general case in 2012. So they proved that. So we'll have the same setup as before. So if the UK norm of f is bigger than delta, then there exists G such that, so we'll have two properties. So G is a degree k minus 1 bracket polynomial. So this is a degree 2 bracket polynomial. You can add, so I don't demand that there's just a single term. You can add many of the terms. But I want that this bracket polynomial is not arbitrarily complex. So G has, just bounded in terms of delta, 1 many terms. So it's not some like super long expression. So right now I just have some function G. The third condition is that f correlates with G. So f of x times e to the 2 pi I x over n times g of x. This is bigger than some function of that. And this turns out to be an if and only if condition. So okay, there are several remarks here in order. So this was actually the final step in a program of Green and Tau to sort of understand linear equations of the prime. So I mean, given this theorem is extremely useful. If you given this, what they were able to, the authors were able to derive is they were able to sort of. So the Green Tau theorem says there are arbitrarily many, there are infinitely many k-term arithmetic progressions of primes. Given this theorem and a lot more work, you're able to say you can actually count the number of k-term arithmetic progressions of primes. So this is an extremely strong statement, and it's incredibly important to have this fact that you're averaging over the whole group and not sort of just looking at some small sub-progression. That's important when you deal with applications like the primes. But this theorem has one shortcoming, which is that it sort of doesn't give any quantitative information on 2 and 3. So in particular, these functions that weren't even specified. Okay, as written formally, there was no bounds given. So it was a major achievement of Manners in 18, where sort of one can interpret his statement as saying, instead of, so you have polynomial in delta many terms, and your correlation is at least double exponentially good. I hope I got the minus in the right place. And sort of the main technical work for us is sort of to improve this. So what we can show is that you have a most log 1 over delta to the O1 terms, and you have greater than quasi-polynomial correlation. And okay, I mean, given this is sort of the driving force behind giving the improved bounds at Szemerédi. So almost all the work is in deriving this statement. So in some sense, we've given a quantitatively stronger version of this. So you can think of this as deriving some algebraic structure. Your function f, you just know it has some kind of like large analytic norm, and then you get that you correlate with a really algebraic object. And the main point of our work is sort of give a quantitatively stronger version. Okay. So the last 10 minutes of the talk will be dedicated to sort of pretending to say something about the proof of how this goes, and maybe just to sort of give a general feel of how one attacks these problems. Okay. And much of what I'm saying is it's really not maybe due to us. It's sort of there's the work of Gowers and the work of Greentown and Zebos. Much of what I'm saying is just sort of giving a conception of how one starts to attack these problems. So, so the proof. So these things have inductive definition. So it proceeds by induction on K. And sort of we've handled the case K equals 2. So the simplest case is K equals 3. Okay. So what do we have? We have that the U3 norm of F, this is bigger than delta. So this implies, just by unwinding the definition, that that many multiplicative derivatives delta H of F, these have large U2 norm. So in particular, the average over F of U2, this is bigger than delta to the O1. And so now we can just apply the U2 inverse theorem on the inside. So there exists theta H such that the expectation over H, so for each inside function, I'll get some different Fourier character I correlate with. So del H of f of x correlates with e to the 2 pi I theta H over. Okay. Let me write it as 2 pi I theta H. This is bigger than some delta to the O1. At some point, I will start lying and just writing bigger than 1. Okay. So at this point, I just have these frequencies theta H, but they don't have to talk to each other. I just have one frequency for each element H. So there's a magic Cauchy-Schwarz argument of Gowers, which says you can sort of relate these theta H to each other. So what he proves is that for some polynomial number of additive tuples, H1 plus H2 equals H3 plus H4, we have that, so you'll have that theta H1 plus theta H2 minus theta H3 minus theta H4. This is approximately equal to 0. So I mean, this is a very surprising connection. So we've sort of been able to forget about this function H and derive some structure on the thetas. We're able to say that it looks, so for many additive tuples, the thetas act like they're additive. And this is a situation that additive combinatorialists are happy with, so in particular using a tool known as Ball and Szemerédi Gowers, and then things towards the so the Freiman-Grusha theorem. And really, it's quite important for us that we're sort of, since the work of Green-Tau-Ziegler, there was a really important improvement here due to Sanders. And what you can show is that theta H, such functions can't look completely arbitrary. So theta H will look like something like alpha I times the, so this is the integer part function of H times alpha I. And you won't have this for all H, but you'll have this for many H with D, which is very small. So log 1 over delta. So you can now take this and plug this in back here. So what does this give you? This gives you the expectation over h, expectation over x, del h of f, e to the 2 pi I, the sum over I equals 1 to d of alpha I x, beta I h. This is large. I'm going to start forgetting about quantitative dependencies at this point. Okay. So this doesn't, I mean, this isn't the statement of the U3 inverse theorem, but we've made a remarkable amount of progress. I mean, this sort of, I mean, okay, this kind of looks like a bracket quadratic expression. And so, I mean, it's, this seems like we have I've just, yes, you just plug in theta h here, and you get this expression. So we've made some remarkable amount of progress. This looks like some kind of bracket expression, like degree 2 bracket polynomial. And okay, there's an argument of Green and Tau called symmetrization, which given star, one can derive the U3 inverse. And okay, so this is the case k equals 2. I mean, this is really an honest summary of the ideas that go in. Actually, justifying each of these steps takes a bit of work, but I mean, the U3 inverse theorem is somehow substantially simpler than the higher cases. But okay, this is, so maybe to hint sort of what happens, like why does this become more difficult? So let's sort of, so what happens when k is bigger than 3? Okay, so you can try to run the same strategy. So if you have that your U4 norm is large, so let's just do the case U4, that's pretty indicative. So say the U4 norm is bigger than delta, then you have that the expectation over h, the U3 norm of the multiplicative derivative, this is large on average. Okay, so now we see the first problem. So instead of a Fourier character, you now get these ugly bracket quadratic expressions. So there exists GH, which are bracket quadratic, such that the expectation over x over h, the expectation over x, del h of f of x times gh of x, that this is large. So instead of having this Fourier character, you get some other type of functions, and they're certainly not as easy to deal with. And sort of the work of the proof is sort of is to show that the GH line up in a reasonable way. So I'm not really going to say anything about this, other than to point out where sort of maybe where the main tools are that are coming in. So it turns out, let's just notice something. It turns out how you derive this conclusion that theta h1 plus theta h2 minus theta h3 minus theta h4 is approximately equal to 0 is that you try to understand when expressions, so we have this basic fact that e to the 2 pi I x dot theta h over, this average is large if and only if theta h is roughly equal to 0. So an exponential phase, its average is only large if this if the phase is sort of close to 0. And we need an analog of this for these uglier functions gh, for these bracket quadratics. So this quickly leads to a topic called that goes under the name equidistribution of nil sequences. So the first people really to give quantitative information here is work of Green and Tao in 2012. But maybe a key point in our work is to sort of not use this result, but a later work of one of the authors, James, which gave substantially improved bounds for the equidistribution of nil sequences. And that plays a crucial role in the proof. The other sort of main quantitative improvement that's coming in is sort of this work of Sanders. So and it's also important to mention work of Kroot and Sisas, which plays a crucial role in the work of Sanders towards the polynomial Feynman-Rouget conjecture. So in some sense, these are the two main quantitative tools that let us sort of prove our theorem. And they're really the heart of it. And so that's one large part of the proof. And that's sort of the main quantitative refinements that's happening over the earlier work of Green, Tao, and Ziegler. Okay, that's actually all I had planned to say, so thank you. So one thing you want to understand for this proof I'm going to claim is sort of you want to understand when the average of, say, e to the 2 pi alpha x times when this is large. So understanding it in this form is very difficult. The correct thing to do is sort of to write this in the form I said earlier. You view it as a function of the Heisenberg group, g to the n times gamma. And it turns out that this condition, you derive some algebraic condition on g. It sort of, in some sense, lives in the abelian part. I'll be slightly imprecise. It lives in some abelian part. But that algebraic, sort of understanding when these things are large, it looks like an analytic problem, but the answer is very algebraic. And that's sort of why this perspective is useful. If you write it, I mean, these things are formally equivalent, so I could write a condition here, but it would look completely unnatural. This sort of explains where it's coming from. That's sort of why this perspective of, basically the notion of a subgroup is incredibly important. That's why you need the algebraic perspective.
You must be using something more, right? Because even for the U2 norm, you get the best bounds for all of these, and you're always not the standard bound you get is better than the wrong argument, right?
Yeah. So okay. This is roughly what Heath, Brown, and Szemerédi noticed. What you can do is you can say, okay, if you run a little bit more, instead of having just one Fourier phase, you can just find sort of all the Fourier phases you correlate with simultaneously. You basically say, you remove off the, okay, so you get all these Fourier phases, and then what you can say is you can find some long arithmetic progression on which all of these phases are constant, or like close to constant, just by like some Dirichlet argument. And this turns out to give you a log type bound. And that's exactly what we do. We just, because you can sort of run this argument because you have a global correlation. So the reason Gowers can't do this is that he doesn't have a global correlation. But once you have a global correlation, you can sort of group together phases.
That's how you get something
No, we get something worse. E to the log to the ck is yes. Yeah, this is a subtle point. yeah. In some sense, they run a slightly more efficient. They run a much more complicated, but in some sense, more efficient version of this argument.
Somehow the reduction doesn't go from endpoint to some constant.
So it goes from n to some constant, but instead of going from alpha to alpha plus alpha to the O1, you go from alpha to 2 alpha. So in general, I mean, for almost any density increment argument where you have where you can establish an inverse theorem, which is global, you can sort of group together your phases and get this multiplicative density increment. I mean, this holds an almost complete generality. It's sort of it's an argument essentially of Green and Tau. This proof does not work. Sort of the corresponding algebraic problem is different. It's sort of understanding polynomials, and various parts of the proof just don't make sense. I think so. Luka Milicevic has now done the case of the U4 norm with quasi-polynomial balances. The proof is quite different, obviously quite a bit harder. So yeah, it turns out for these higher Gowers norms, it's much harder to do the finite field case. There's actually a very simple reason. There are not so many Heisenberg groups. There's like very few of them. There are lots and lots of polynomials. Because there are so many polynomials, this makes the problem much harder. That's essentially why the problem is harder. A small characteristic has its own intricacies. Let's not discuss that. So I think for the U4 case, you can prove in small, like in the F2 to the n, but higher characteristic is easier always. You don't just get polynomials; you get these things called non-classical polynomials, and yeah, they're fiddly objects to deal with.
So the issue is with the equity distribution.
So okay, essentially what you can do at this step is that we get these functions on various nilpotent groups. It turns out that there are just not that many nilpotent groups. I can sort of assume that all my functions come from the same nilpotent group. That's just not true over finite fields. And so you need to prove something much harder. There's sort of a more complicated algebraic abstraction. And that's sort of the first line of this proof. And that's why it doesn't work over finite fields. You need to replace it by something else. The proof vaguely follows this strategy, but it's quite different because of that feature.
There's a lot of feedback.